Today, it's an exciting day. It's the start of the student presentations, and Francesco is going to take us through electronic noses and cancer, a sniff that can save your life. Take it away, Francesco.
Hi, everyone. Today I'm going to talk about the electronic nose technology and the application in cancer detection. So let's start with a rapid overview on the cancer situation here in Canada. So the lifetime probability to develop cancer is 45% if you're a male and 41% if you're a woman. And cancer is the most lethal disease, as 30% of all the death due to diseases due to cancer here in this country. So if we take a look to the statistic, the prediction from Canadian Cancer Society for the last year, we can see that for males, the most common type of cancer is prostate cancer, and this is the third most lethal. And for females, breast cancer is the most common type, is the second cause of death for cancer. And lung cancer is the third and the second, respectively, for males and females in terms of incidence. And in both the cases, the most lethal type, with 27% for both the genders. So for this kind of disease, the screening, what we call screening, is looking for cancer in asymptomatic subjects, is really important, as the early detection of the disease can really change the therapeutic outcome. Because if you treat the cancer in the first stage, the probability to have a successful outcome is much higher. So currently there are different screening techniques. I will concentrate on these three kind of cancers because, as we see, they are the most common and most lethal. There are different screening techniques that have been used, like, for example, lung cancer, the best option is the low-dose CT scan. For prostatic cancer, there is the PCA test and the digital rectal examination. Or for the breast cancer, there is mammograms or magnetic resonance imaging. But all these techniques suffer of some limiting factors that are the difficulty of scalability over a large number of subjects. Some of them are invasive and they can be source of harmful radiation. Let's think about the CT, for example, the chest X-ray or the mammogram. These are X-ray and they can be really painful and uncomfortable for the subject. Let's think about the mammograms. It can be really painful for the woman. As well as the cost of this X-rays is usually high, and the time required for the analysis is not really fast. And more importantly, the sensitivity and the specificity cannot be really good at the same time, usually, for these techniques. So these limiting factors may make these techniques as not suitable for very extensive cancer screening campaign, theoretically over all the population. There is this fact that the cancer triggered the production from the body of some volatile compounds called volatile organic compounds that can be detected in the fluids of the patient, like breath or urine. And we can see in this image on the top, two of them. These are two volatile potential biomarkers for lung cancer. And actually, there were a lot of studies that have been made for detect different type of cancers. You can see lung, prostate, leukemia, lymphoma, breast, and colorectal cancer using spatial patterns of this kind of box. And the study were successful. So today, the current bulk analysis technique is called gas chromatography and mass spectrometry. That is a lab technique, has a good sensitivity and specificity, is not invasive. The problem is that it's time-consuming technique because it's a lab test, and the performance in distinguish different stage of cancer are really poor, actually. So that's really important because you can change the strategy of treatment depending on the stage on which the cancer is detected. So it may be as well not suitable for large screening. So I read this fact that for me was really surprising because everyone knows that the domestic dogs has a really good olfactory system, much better than the humans, but I didn't know that they can smell cancer. And apparently, if you train a dog in a very well manner, they can reach a really good performance, up to almost 100% for sensitivity and specificity for lung cancer. There are some problems associated with that because even if they can reach this performance, the dogs' results are really heterogeneous. They are living systems as us, so there are differences. There is an implicit heterogeneity between a dog and another, even if they are the same race. So, and the training is long and expensive. So the training is similar to the one that they use for explosive detection or narcotic detection canine teams. And I will show you a short video on YouTube that will is from Cancer Dog Canada that will show you how they are trained. So as you can see, it's really similar. If you ever seen how they train the dogs for narcotic detection, they basically put the dog in front of some samples, and the dog has to recognize the right sample. And if they recognize the right sample, the prize given from the instructor will be some food. So as you can see, in this case, they have probably some cancer-smelling samples, and when you will find the right sample, it will receive a prize, a present from the instructor. But as we say, this may not be the best option. So the idea is to translate the performance of the olfactory system of dogs in artificial bio-inspired systems. They can be trained just once. They don't need to be trained every time. They are not heterogeneous. And that actually was made in the early 60s when they invented the electronic nose. Electronic nose was initially developed for food and beverage industries, and then the use was extended to different fields like pollution control, microbiology, and disease detection, of course. Here in the second part of the slides, you can see a general structure of electronic nose. So there is a sampling system where the samples are collected from the environment and then eventually filtered, and then they are sent to a sensor array. Every sensor in the array is going under a reversible change in one of the electric properties due to a specific Vogt binding. So basically you will get a different electric signal depending on the set of Vogts that are, so the type of smell that is in contact with the sensor array. And then the signals coming from the sensor array are sent to a pattern recognition system where the signals are elaborated and a classification is made. So they say, for example, if this signal is coming from the sensor array, this is the set of Vogs that is binding, and this is the, for example, the pathology that is present in this subject, and so on. So regarding lung cancer, the nano-artificial nose is probably the most promising device. It was invented by Professor Osama Eik at Technion, Israel Institute of Technology at Haifa, and they test 3 different strategies for the detection system that are functionalizing microelectrodes with biocapped gold nanoparticles, use network of single-wall carbon nanotubes, or using chemical-sensitive field effect transistor based on silicon nanowires. Regarding the pattern recognition system, they used several algorithms such as principal component analysis, artificial neural networks, or cluster analysis. And here in the figure you can see a typical setup for the breath analysis. And here is where the subject has to breathe. And this one is the whole device. As you can see, the size is reduced, but it's not really small. It's something like comparable to a desktop of a computer. And this one is the detection system. As you can see, the scale is just 2 centimeters, so it's really, really small. This one is one single electrode. As you can see, the detection system is really small. Why this electronic nose is innovative? Because the sensors are cross-reactive. So they can recognize a broad spectrum of Vogs. It's not highly selective. So you can use for a lot of different applications. The technique is really easy to perform, so anyone can do, even yourself, you can do at your own, or a clinician can do without any special training. The analysis is extremely fast, and they prove that this technique can also discriminate between benign and malignant pulmonary lesions. So basically you can distinguish some precursors of lung cancer and distinguish that from already set cancer. Actually, the market translation is enacted as a US company patented this technology, and we expect to see that in a few years. Now they are testing, I think is under clinical trials or something like this. And another interesting application is that there is this project, it's called Sniff phone project. It has been funded from the European Commission, and it's basically the goal is to miniaturize and integrate this device in a smartphone. So everyone in the future can do his own cancer screening even every day at home, just using this device on your smartphone and eventually an app. The same technology has been tested successfully for breast cancer detection. Here in the figure you can see, the figure on the left is the smell fingerprint of breast cancer breed. So as you can see, there are, on the x-axis you have the type of box, and on the y-axis you have the abundance. And as you can see, there is a well separation between healthy subjects, healthy breasts that are the white one, and breast cancer subjects that are purple. In the other figure, you can see a typical response for the sensor array, that is the change in the resistance, in the electric resistance due to the breathing of the subject. As you can see, there are 5 different signals. You have lung cancer, colon cancer, breast cancer, prostatic cancer, and healthy, and the responses are all different. And this is how this technology works, how the sensor array works. The same version of the nose has been tested, including also nanoparticles made by platinum. And again, it has been tested for discriminating between benign breast lesions and malignant breast lesions and healthy tissues. And it worked very well. So it's potentially able, again, to detect breast cancer precursors as benign lesions. And so it can be used to a kind of pre-screening. So screen the risk of cancer before you have already a malignant lesion. Okay, so for the prostate cancer detection, also for this topic, a lot of different projects have been made, like the nose has been tested successfully for that. There is this other ENQB nose developed at the University of Rome that was using quartz crystal microbalance functionalized with organic compounds for prostate and bladder cancer, where basically the working principle is when a VOC is binding with this microbalance, the mass will change and the oscillating frequency will change, so you will have a different electric signals. And then more recently, there is this study that tests the use of a commercially available eNose, that is the KimPro 100 eNose, has been tested for discriminating between prostate cancer and benign prostate hyperplasia. That is a benign pathology of the prostate that can be easily confused with prostate cancer. So again, they analyzed the urine headspace, and they found it working really well in being distinguished the two pathologies, and that can reduce the overdiagnosis or the underestimation. So as these two pathologies can be easily confused, the overdiagnosis is when you say that someone has just BPH, but the clinicians say that he has prostate cancer, so he will go under surgery, and it will be really bad if he doesn't have cancer, or even worse, if he has cancer, they think that he has just BPH. The problem with this study was that it was not X and healthy subjects, so they need to experiment more because the population is likely composed also by healthy subjects. Okay, so I will present now 3 future possible perspectives of this technology. So the first one is, I can see a role of the electronic nose in the global health, as a lot of diseases have been associated with a particular unique smell. And some of these diseases are really, really common in poor and remote areas of the world. For example, let's take the example of the yellow fever. Yellow fever is really common in Central Africa and South America, and it's causing like 30,000 deaths each year. And the current diagnosis techniques are based on blood tests. So it's difficult in a remote village to do a blood test, right? Because you don't have a lab, you don't have the fridge to conserve the blood, and so on. This disease is associated with a butcher shop smell, really intense. So that can be, the nose here can, as is a cheap technology, is portable, and you don't need any lab to do that. It just, everything is automatic. Or tuberculosis, again, really common in poor zones of the world. There was this project that was founded by Grand Challenge Canada and Bill Gates Foundation in 2011 to develop in India a nose for tuberculosis detection in order to substitute the sputum analysis. That again is time consuming, and you cannot do that in remote areas where you don't have a wet lab. Another photo perspective, that in my opinion is probably the most amazing, is integrate the fruit fly olfactory system in electronic nose. They found that the Drosophila melanogaster olfactory receptors that are located in the antenna, they can recognize different dangerous chemical components And more importantly, they have a unique activation due to the exposition to breast cancer cells. And that's really interesting. As you can see in this figure on the bottom, the second and the fourth lines are related with the in vivo calcium imaging for the Drosophila antenna exposed to cancer cells. And as you can see, the activation is much stronger than the healthy subjects or the nitrogen environment. So why this discovery is important for the eNOS technology? Because the insect receptors, our biological receptors, are much faster than the chemical artificial sensors. The scale is like milliseconds. And then one antenna can contain up to 300 receptors versus just 20 that you can find in a normal sensor array. And the spectrum of recognized smell is huge because, as we know, even us, we can smell a lot of different smell, much more than an array. And also they're adaptable, so they are not influenced by external confusing factor or humidity and so on. So we may see an electronic nose that they will integrate something that can artificially imitate the olfactory receptor of the fruit fly, or include even real fruit fly olfactory receptor inside the nose, the electronic nose. And then the last that I'm going to present is really interesting as well. So is the possibility to develop a quantum-based nose, because the classical theory of smell is the lock and key principle. So if your smelling compound has a shape that is matching the binding site shape of the olfactory receptor, we recognize that smell. But that cannot explain everything. So in 1989, the biophysicist Luca Turin proposed this quantum theory of smell, saying that the smell recognition is related with the vibrational frequency of the smelling compound that has to match exactly the difference between an electronic donor and the energy of an electronic donor and the energy of an electronic acceptor within the binding site. And then an electron can eventually travel through these smelling compounds through indirect quantum tunneling. And that can explain something that the classical theory cannot explain. So for example, why if you replace in a molecule, you replace one atom with one of its isotopes. So you're just changing the mass, so the vibrational frequency of the molecule, but not the shape. This can smell differently. This is not still unclear. There are studies that demonstrate that the human can distinguish between two different isotopic replacement molecules, and studies that say the opposite. So it's not really clear. But this can also explain why molecules with completely different shapes can smell similar. For example, all the molecules that include sulfur and hydrogens bind together, they smell like rotten eggs, but they can have really a lot of different shapes. So the theory is still debated, but if it's correct, if someone will build a quantum nose, the selectivity can be just modified through a bias. So you will just change artificially on your sensor the vibration energy on which the sensor is tuned on. Okay, so you will change just the energy of the donor and the energy of the acceptor, so you will go to another frequency. And you don't need to modify the sensor. You can have a theoretically infinite selectivity. You can change just applying an electrical bias or something like this. So it will be superior to any chemical sensor-based nose that now we have. And there is actually a research team in Imperial College London that is developing a device that is based on indium arsenide and indium phosphide nanowires that can actually work with this principle. So we will see if the theory is correct. But the theory, I repeat, is still debated, so it's not, we are not sure about that. So the conclusion of the electronic nodes applied to cancer and also to disease detection is that, in my opinion, they are the most promising clinical translation of the exceptional ability of the dog to detect cancer from the smell. It can be a really big step ahead for cancer screening because it will be much faster and cheaper. You can screen maybe all the population. You can do the screening at your home, right, with a smartphone. And it can change totally the rate of survival of patients because now it's really low. The survival rate after the treatment is low. And there is the possibility to extend this to different diseases, really different. You see, Alzheimer, Parkinson, there are studies that are going in this direction. So completely different, neurodegenerative, kidney disease, gastric disease, cancer, and so on. And as well as this technology can be easily used in remote and poor zones of the world. And as we see at the end of the presentation, there are exciting doors that are open for further improvement of this kind of technology, passing through genetic engineering and biomimicry, as we saw in the case of the fruit flies, and quantum physics, as we saw in the last slide. So I think that the future of these devices in the health system is really, really bright. And so these are the reference of if you want to learn more on the papers where I took the information for this presentation. And it's one of the figure and video sources. And yep, and that's all. So now if you have any questions, I will be glad to discuss with you about that. Thank you. Thank you for your time.
This is just kind of on the spot. I was just wondering, I've heard recent technology about how similarly things can be applied with taste sensation. Do you know anything about that?
Sorry, can you repeat just because?
Taste as opposed to smell.
Oh, actually, I know. I mean, when I say that this technology was developed in the first time for the food and beverage industry, that was for tasting the smell. And I know that they developed also an electronic tongue. So that's the kind. The thing is that it's probably much simpler for cancer detection or disease detection to try to study the breed, because it's simple to collect and the device is simple to design and to build and as it's cheap. I don't know anything about an electronic tongue, but about an electronic tongue for this topic, but it may be. I know that this kind of device exists, but I don't know if they have been ever applied for clinical.
And then my other question was, so you were talking about how like smell operates kind of out of a lock and key model, and how right now this is primarily being used for diagnostics, correct?
Is that, can you?
Through diagnostics. So I was just wondering if it was possible that this technology could be applied to treatment as well, wherein like an individual maybe smelled something and the sensation of smell was associated with something therapeutic.
That's an interesting question, because so basically what this technology is doing is taking something that is coming from you. It's not like sending something on your body. It may be, I guess, if you, for example, if you use a treatment on for example, use a treatment for, I don't know, lung cancer, and then after, sometimes you try to do the test with the nose, you can see maybe the improvement of the improvement of the organism, I mean, the repair of the defeat of the cancer to this. I know, for example, for the prostatic cancer, when they use, I was citing this ENQBE electronic nose, and they test on people that went under surgery, and then they see that after first they have prostatic cancer or bladder cancer, then after the surgery, after 2 months, they did the nose analysis again, and they found that the vox were changed because there was a change in the situation. So I don't know if there is any direct application to the therapeutical approach, but it may be something to study, the therapeutical approach, yeah, for sure.
Cool, thank you.
My question is, I'm not sure if you mentioned if this will be a conclusive evidence to use the e-nose, and if the e-nose detects a cancer in someone, then that will not be our only evidence to diagnose the person with a cancer. Because when you brought the statistics for the cancer detector dogs, some of them had up to 99% sensitivity. So do you see a future where the e-nose can be used as a conclusive evidence to diagnose cancer in someone? So
the dogs, when I say the dog has like almost 100% was one study. They say the results are really different. I remember there was this study where they tried to use dog for bladder cancer, and they found that it was 40%. So it was really low. Then there was another study, and there was another study, and they have 100, and another one they have 90, and another they have 70, and so on. So it's really different. It's really, they reach once. But the thing is also we have to guess about the number of subjects, you know, because if they have like just, they test like again versus 10 subjects is not really significant from the scientific point of view. And I may say that For what I know, like the performance of the e-noses for now, they cannot reach the best performance of the dogs. But these devices are not yet in the health environment, right? So they're still trying to improve. But I think that they reach like around 90% of sensitivity and specificity, for example, to distinguish between benign lesion and malign lesion of cancer. So this is really, I don't know if a dog can do this distinction. And the dog, I don't know if they test the dog to see if they can distinguish between a benign lesion or actually a cancer. They just use cancer subjects with already cancer onset. And also the thing is that the electronic nose can tell you in which stage is the cancer. The dog can smell you even in the first stage, but it cannot say this cancer is already on the second or the third or is the zero. You can feel that because usually in the first stage is asymptomatic for what I know. But in terms of sensitivity and specificity, I think that they reach better results with the dog, but it was just once. It's not repeatable, okay? So you cannot trust that for large screening. It was once, but then the other time can change because they are heterogeneous organisms. So this is why.
And I have one more question. So how do you see, how do you predict the sociological implications of this device? Because if an individual owns an e-nose and if they detect their own cancer,
Yeah, I was thinking about that, but so what is today is when you go to do a cancer screening and they found cancer in you, they will say, you will be upset, right? You say, oh, I have cancer. But I'm thinking about like a future when you have your own e-nose at home, eventually on your smartphone, and you will do this every morning, and one day you will get, oh, you have cancer in the first stage, and you will be happy because I say, no, not happy, but we'll say, oh, I take this in time, so the treatment now can be successful. So this is what if you have something that you can do every day, or you can do, I don't know, once a month or something like this, it's not good to know that you have cancer. But at least you know that you find cancer in the first stage, you have more possibilities. Now when it's usually asymptomatic, so when you start to feel something, the cancer is already on a stage that is difficult to treat, right? So this is what I think. It may be good for the social impact of that.
Can this device tell us what stage is the cancer?
Yep.
Okay, how?
It's usually related. Okay, so they cannot just say that. They can also say, for example, for breast cancer, usually there is usually some precursor lesions, like for example, benign lesions in the breast, and then can distinguish between this condition and a malignant condition. So when you have already cancer. And I think usually if you are talking just about cancer, so the stage of when you have already the malignant lesions and is starting to grow, they can, and this usually for the percentage of VOX. If the cancer is a later stage, you will see that the typical pattern, the typical abundance of VOX will be much higher, right? Because you have more cells that are producing that. These VOX are produced by the cancer cell. This is proved. They publish a lot of studies about that. So when you have a late stage of cancer, you have these VOX that are normally not present in low concentration. Then when you have cancer, they increase, but this depending on the stage of cancer. Okay? Does it make sense?
Okay, thank you.
Okay. So thank you very, very much, and we'll go on to the next presentation.